Yeah, where's Colin? Is Colin here? Is he? Okay, well, anyway, Colin asked if there will be a review session, and I I cannot hold a review session for the next exam. Like I don't have the time, to be honest. But good news is that I already have a review session for this exam, and I can post it today. I have the notes for it, and I have the recording for it. It's a review session that I held last year for exam 4, so I can post it. Oh yeah, there's Colin. I just saw Colin. Yeah, so y'all can thank Colin for that. Where did he go? He just logged out. So, oh, there he is. Yeah. Yeah. Okay. So this exam, I don't think it's really intense. I would say the only intense problem is the one where you have to find a power series for ln of. We did an example. I think power series for ln of 10 plus x it was. The example that we did, that is the only long question. But I will include an example. I mean, I have included an example in the review. I have the review here. I was looking through my notes last night after Colin's email, and yeah, let me see, where is it? Oh. Oh yeah, there we go. So yeah, in this review, I did power series for ln of 5 plus x. Okay, we did ln of 10 plus x in class. Okay, so more examples. I will post this later. But let's continue with the polar coordinate system. I don't think we're going to get to finish this today, but we are trying to determine what this is the graph of, what graph this thing will generate. Okay, a is some non-zero number, and we see here a cosine theta as a factor of this polar function. And again, we know that if there was an r in front, then that would be x. So you multiply this equation by r, you get r squared equal to a r cosine theta. R squared is x squared plus y squared, and this is just a times x. And I said, in case you don't recognize this graph, this is the graph of a circle. It is a shifted circle. It's not centered at 0, 0. If you have a number like just a or a squared, that would be a circle centered at the origin, but this is shifted. So to determine the center of this thing, we're going to, of course, determine the shift. And to do that, you have to complete square. Okay, a shift is when you have, like, let's say x minus h squared plus y minus k squared equal to radius squared. Okay, this is a shift h units, k units, h units in the horizontal direction and k units in the vertical direction. So to complete square on this, what you have to do is you move this ax over to the left and group it with x squared. Okay, we're going to rewrite as x squared minus ax, okay, plus y squared equal to 0 on the right-hand side. Okay, And we need to add a term to this this thing so that this group becomes a perfect square. I'm not sure if you have done completing square in algebra, but what you do is you take the middle term. The middle term is negative a. You divide that by 2 and you square it. And that gives you a squared over 4. So what you do is you add a squared over 4 to the left and a squared over 4 to the right of the equation. Okay, and this way, this trinomial is now a perfect square. Okay, this right here, if you factor that out, you get x minus a over 2 times x minus a over 2. Okay, you can check. If you FOIL this out, you get this back exactly. Okay, plus y squared equal to a squared over 4. Okay, so if I rewrite that as a perfect squared, it is x minus a over 2 squared plus y squared equal a squared over 4. So the Cartesian form of this thing is this equation. This equation transforms from polar to rectangular to this equation. Okay, which is, this is a circle because of the squares. The center is a over 2, 0, because you have x minus a over 2. And the radius is, this is the square of the radius. So the radius is at a over 2 also. Okay. Yeah, so let me just summarize. R equal to a cosine theta is the same as okay, which is the circle of radius a over 2 with center at a over 2, 0. And this is a must know. I don't know how you're gonna learn this. You memorize it. You can just do all the math. You can try to just plot points, whatever you can do. And we can see that in this example here, cosine of theta, guys, pay attention to that. R equal to cosine theta. The number in front of cosine is 1. 1. So a is 1. A over 2 is 1/2. 1/2. Look at this thing. The center is at half. Okay, and the radius is half. So if you were to pick more points, if you pick more points, it will generate that circle for you. Okay, but let me graph. Try to graph this. What? Okay. So the x-axis would be here. This is the y-axis. Okay, or you could say this is the polar axis. This is a over 2. That's the center, a over 2, 0. And since the radius is also a over 2, then let me just move that a little further out. This is a, okay? Yeah, from this point, you go a over 2 in all directions, okay? Yeah, this thing here is the distance between xy. So you take any point xy, this is the point a over 2, 0, the center, okay? If you find the distance between xy and the center, you get this, okay? And well, the square of the distance is that by Pythagorean theorem. And as you see, this distance is always constant. It's always a over 2. All right. So for example, if you were to graph r equal to 3 cosine theta, okay, this is a circle centered at 3 over 2, 0 with radius 3 over 2. All right. And you don't need to plug points. We no longer need to plug points because we know what the subject is. Okay. Questions?
Yeah, where would the y come in?
Okay, let me try to understand that. What do you mean? Where with the y?
If we're, for example, well, like as we understand r equals a cosine theta, where would the y come in? Would it be like +3, and then we would know to shift the circle up by 3 units?
So first of all, this this doesn't have a vertical shift. This translates to that. I just closed the notebook. Give me a second. This thing translates to that. This doesn't have any. If you're to draw that, it doesn't have any vertical shift. Y is, I'm not sure what you mean by where would y come in, but when you, again, going back to this procedure, when you have this polar equation and you want to transform it into rectangular, so again, what we did, we multiplied both sides by r. We got that. Okay, this r squared, do you agree that r squared is x squared plus y squared?
Yep.
Okay, and here we have a, and then r cosine theta is just x. So, I mean, according to that, based on that, when you complete the square, the center is at a over 2, 0. There is no, because this is just a y squared. It's not a y squared plus or minus anything. Then the center will be on the x-axis. So
would we ever see a shift? And like, let's say 3 cosine theta plus.
Yeah. Okay, so if you add a number to this, by the way, that is not a vertical shift. Do you know why?
No.
Yeah, that's because, again, this is not a function of x. This thing is not a Cartesian thing. If I add a number to this, typically when you add a number to a function, it moves it up or down, right? That's the Cartesian, that's a Cartesian function. This is a polar function. When you add 1 to that, okay, this means that you are increasing the distance from, r is the distance from the center to the points on on the graph, that distance will increase.
So it would just make
As-
the circle bigger.
No, it's not. Well, it's actually, we're gonna see what that does. Okay, that would be the fourth object we're gonna discuss. Okay, so I think that's next one is another circle, and then 4 is example 4. We're gonna add a number to that, and you see what that is going to do. Okay, you'll see that in a second. But so the same guys, the transformation rules, like vertical shift, horizontal shift, vertical compression, stretch, horizontal compression, stretch, those rescaling things, anything that you learn in pre-calculus about how functions, how graphs are impacted when you add a number to x or add a number to y or multiply x and y by a number, those rules don't work here. Okay, they don't work here. If I add a 1, to that, it doesn't move the graph up. Okay, it is doing an impact on r. R is the distance from the pole to the points on the graph. So yeah, imagine if you have y equal to f of x, right? If I do f of x plus 1, this shifts the graph of f of x up by 1. But if you have y equal to some f of theta plus 1, I'm sorry, not y, r equal to f of theta plus 1, this is not a vertical shift. It's not. We are not in the rectangular system. That one does something entirely different. Okay. So next common polar graph is r equal to a sine of theta. All right, just like what we had here, r equal to a cosine theta. This is also a circle, but this is a circle that has a center on the y-axis. Okay, and I want you to prove that. Okay, and I'll show you how to begin the proof. But this is x squared plus y minus a over 2 squared equal to a squared over 4. So just like what we had here, this is a shift on x, this is a shift on y. Okay, this is the circle of, again, radius a over 2, centered zero a over 2. Okay, so this would be a over 2, and that's a. All right. Now, to prove y, you're going to do exactly the same thing as for number 2. Okay. So we have r equal to a sine theta And you want to transform this from polar to Cartesian, just multiply everything by r. You get r squared equal to AR sine theta. Okay, r squared is again x squared plus y squared. And we have AR sine theta by transformation rules is y. Okay, so again, circle, you have an AY, meaning that after you complete square, you're going to move this over, group that with y squared, and do exactly what we did here for the previous example. And you get this equation. Okay. So let's talk about more interesting graphs. All right. Now, certain graphs in polar form, certain polar functions give you really cool graphs.
Professor,
Yeah.
is it r equals a sine of theta? Because I was looking back for the cosine, and we have x equals r cosine theta.
X is r cosine theta, correct. Yeah. Okay. All right. Where did I
think I'm just confused then.
What are you? Oh, hold on. Right. X is r cosine theta. But let's see. What did I write down here? That is confusing. Here
Because
r,
yeah. So r sine is y.
Yes. Yeah.
Okay.
Yeah. So you do exactly the same thing that we did here, but instead of adding the a squared over 4 to the x term, you add it to the y term. You complete the square on y. Yeah. You know, the thing with parametric graphs, we saw some cool parametric graphs, right? And parametric graphs, parametric equations do something that a typical y equal to f of x type of function doesn't, right? I mean, you can draw the parametric curve that we drew, for example. There is no way that you can come up with y equal to f of x that can graph that for you, because this is not a function, this graph. Parametric equations take care of that situation. They take care of that problem. All right. Now, polar functions, very cool thing about them, you just have a single equation, a single polar function whose graph is not a typical function of x. Okay. In Cartesian form, this is not a function, but in polar form, that is a function. That's a good thing about polar equations. A single equation, unlike parametric equations, that give you graphs that don't pass the vertical line test. You know, r equal to 2 plus 2 cosine theta. All right, so here we're gonna actually plot points, guys, because trying to convert this from polar to Cartesian by what we did previously is not easy. You can, if you want, you can multiply everything by r. You get r squared equal to 2r plus 2r cosine theta. R squared is x squared plus y squared. Okay, that's good. But 2r is the square root of x squared plus y squared, unfortunately. And there's a plus or minus, because r squared is x squared plus y squared. When you take square root, you get two solutions. And then we have plus 2r cosine theta is just x. This is not nice at all. I mean, no one can look at this and identify the graph. Okay, So converting into a rectangular, it works. We can convert it, but it is hard to identify the graph. Okay, so we're just gonna plot points. All right. And we'll plot points from 0 to 2 pi. Why isn't that? Let me see. Okay, so begin with 0. Plugging 0 here, you get cosine of 0 is 1. 2 plus 2 is 4. All right, I'm gonna pick pi over 6. You have to be a little patient. Okay, pi over 6, that gives us 2 plus cosine of pi over 6 is root 3 over 2. So 2 plus 2 times root 3 over 2, which where those 2's cancel out, you get 2 plus root 3, which approximately is 3.7. Okay. We'll plug pi over 4. We get pi over 4 here. Cosine of pi over 4 is root 2 over 2. These cancel. Root 2 is about 1.4. Add that to 2, you get around 3.4. Okay, so as you see, the value of r is getting smaller. 4, 3.7, 3.4. Okay, let's pick pi over 3. We get cosine of pi over 3, which is 1/2. So 2 plus 2 times half. That gives us 3. As expected, r is getting smaller. Let's pick pi over 2. Cosine of pi over 2 is 0. That gives us 2. Let's pick more angles. Let's pick 2 pi over 3. I will show you guys a much faster way to graph because plotting points is not a lot of fun. 2 pi over 3. Cosine of 2 pi over 3 is actually -1/2. And that gives us 1. Okay, 3 pi over 4. That's 2 plus 2 times -√2 over 2. And that is 2 minus 1.4, which is around 0.6. Again, r is getting smaller and smaller. Let's pick 5 pi over 6. That would be 2 plus 2 times -√3 over 2. And this is around 0.3. If we take pi, we get cosine of pi is -1. So 2 minus 2, that gives us 0. Okay. So I'm just going to stop here. Okay. You can pick more points from pi to 2 pi. Okay, but at some point I will use symmetries here. And next example, I will show you how to graph this without plotting points. Okay, you just have to have a little bit of skills, some skills in trigonometry, basic skills in trig. That's big enough, huh? Okay. So let's see. Yeah. This is 1, 2, 3, 4. Okay, so every one of these is 1 unit. All right, beginning with the angle 0. You go 4 units in that direction. So this is theta of 0. And oh, by the way, the good news is that none of these r's are negative. Okay, we are not dealing with a negative r where you have to go inward. All right, the opposite direction of the terminal side of theta. So that makes the problem easier. So when theta is 0, you go 4 units. That's 1, 2, 3, 4. Okay, we're talking about this point. All right, the point is 4 for r and 0 for theta. Okay, remember, this is r, this is theta. Do not confuse this with xy. This is just a coincidence that xy here is also 4, 0, okay? Next point is at pi over 6, 3.7. So here's pi over 6. We're gonna go 1, 2, 3. This is 4, so 3.7 is right around here. Hold on, guys. Listen, get out. So pi over 6, 3.7. I got that backboard. That's 3.7 pi over 6 is what I meant to write down. It's first r and then theta. Okay, next point is at when theta is pi over 4, we get 3.4. Okay, so this is the pi over 4 angle. You go 1, 2, 3.4 is right around here. Okay, and next point is at pi over 3, 3. Pi over 3, you go 1, 2, 3, right there. Okay, and then we have pi over 2, 2. So at this terminal site, you go 2 units, 1, 2. All right. So far, if you connect these points, we get something like this. Okay, what is happening is that the distance from the pole to the points on the polar graph gets small and smaller, okay, as you're approaching pi over 2. All right, and they get smaller than that as you get closer to pi. So at 2 pi over 3, we have 1, here's 2 pi over 3, and 1. So it gets increasingly more difficult to locate these points because r is getting close to 0. But right there. Okay, next we have 3 pi over 4.6. Here is the angle 3 pi over 4. Okay, and you just go 0.6. Okay, so 0.6 right around here. And I'm running out of room actually to write down the coordinates of the points here. All right. We can talk about the derivatives later. We're just doing the basics. And then we have 5 pi over 6.3. Here is 5 pi over 6. You just go a little bit, 0.3. Good thing about having an iPad is that you can zoom or a tablet. And then at pi, r is 0. So at there, we're going to be right on the pole. Okay, so if you were to connect these points, that's what we end up with. All right. Now let me just move that point a little further out. Okay. So if you continue with the drawing, you get the same exact graph, but reflected around the horizontal axis. Okay, you can try out if you want. So for example, if you plug in, let's just plug a point. Let's say we plug something easy, like let's say 4 pi over 3. Okay, 4 pi over 3 is this angle. At 4 pi over 3, we're going to have 2, again, 2 plus 2 times -½ and that is -1. Okay, at 3 pi over 2, you get 2 plus 2 times cosine of 3 pi over 2 is 0, which is 2. So
So
here's
is that -1? I think it's just 1, right?
it's just a positive one, exactly. Yeah, as I said, r is at no time going to be negative. So here is 4 pi over 3, and we're going to be at 1 or 1 unit away from the pole, which would be that point. Okay, and at 3 pi over 2 will be at 2. Right there. So if you connect, you get, again, as I said, the symmetry of this piece. Okay. Yeah, for some reason, we have 1, 2, 1, 2. Yeah, that's fine. Yeah, and if you complete the graph, it's just going to be, again, I should just plot points and not go through the pain of correcting this like a million times. But we're going to show you a better way to graph these, okay, in a second. All right, this is called a cardioid. Well, because it looks like a heart. That's what this object is. Okay, so I'm not sure who asked, well, I don't think anyone asked, but as you see, if you add a number to a polar function, it doesn't shift the polar function. It does something entirely different. It's increasing your R by that amount. Okay, but yeah, so again, here is the distance from the pole to any point on the polar graph. That distance is at a maximum of 4 when theta is 0, and as you get close to the 180-degree angle, that distance gets smaller and smaller. R is getting smaller and smaller. Okay, and then from pi back to pi over 2, R starts getting big and bigger. All right, this again, it's a cardioid. You know what, I agree with you. Someone says it looks like a butt. Jose says they should have called it something like that, you know, instead of a cardioid. Asioid, I don't know. What is the technical scientific name for butt? Exactly, Ahmed. Yeah. Yeah, so how do we know if the graph is going to be a cardioid? Cardioids happen if you have R equal to A plus A cosine theta or r equal to a plus a sine theta, just like what we have here. A plus a cosine theta, or a plus a sine theta. If you graph this polar function, it is a cardioid that will look like that. Okay, this will be symmetric with respect to the vertical axis if you draw it. Polar, but you guys are funny. Yeah, so those are cardioids, okay? Let's go over the next graph. And again, I'm gonna show you guys a much better or much faster way to graph, okay? We are not yet using derivatives here because we haven't talked about the derivative of a polar function yet, okay? But next we're gonna have, so this is example 5. The next class of graphs is when these numbers don't match, okay? Yeah, notice that the amplitude, so if you think about this using basic pre-calculus, the amplitude of this cosine function is from -2 to 2. When you add 2, you are shifting the Cartesian form, shifting the graph up by 2. So this graph is always between 0 and 4, right? R here is between 0 and 4. We saw that over here, 4, and then you get closer to 0. R is always between 0 and 4. R is never negative, okay? But if this number, if these numbers don't match, then R could be negative, especially if this number is less than this number, R could be negative. And when R is negative, something really interesting happens. So let's see. Let's go with R equal to 1 plus 2 cosine theta. Okay, so let me show you the steps for graphing any polar function. And I expect you to graph a polar function in this class this way, okay? Not really by plotting points. All right, so for part A, we are going to find the zeros of R. We're gonna set this equal to 0 and see when R is equal to 0, because if you know when R is 0, then we do know, we're gonna know when the graph is gonna meet the pole. At the pole, R is 0. Okay, so find the zeros of R. Yeah, on 0 to 2 pi, and graph R versus theta, or I should just say theta versus R, in the rectangular form, not polar form. So think of this as a pre-calculus problem, a basic trigonometry problem, not a polar problem yet, okay? And you'll see why. So what I want us to do is to graph the cosine wave. I want us to graph the cosine wave, and from that graph, do the polar version of it, okay? Yeah, and trust me, it's much easier. So set 1 plus 2 cosine theta equal to 0. That means cosine of theta is equal to -½ Okay, and again, as I said, you just need some trigonometry, basic knowledge of trig from the unit circle. This means theta is 2 pi over 3, right? So the reference angle is pi over 3 or 60 degrees because cosine of 60 degrees is 1/2, but angle, the terminal side has to be in quadrant 2 because cosine is negative. So you got 2 pi over 3. Also in quadrant 3, where theta is 4 pi over 3. Okay, so for those theta values, R is going to be 0. Okay, is there a range for cosine theta? Cosine theta is always from, what do you mean range? Range for cosine is from -1 to 1.
No,
But,
sorry. I think like what I was kind of confusing it with is are we like assuming that like this is like simple? Oh, okay. We're given
Yeah,
that. Okay,
yeah. A
cool.
polar graph is generated by revolving theta from 0 to 2 pi.
Okay,
That's enough.
okay, cool.
Yeah, and that makes it, you're right, that makes it simple.
Okay.
Okay, again, yeah. And then what you want to do is to graph it, you want to find the key points. Okay, the key points are the locations of maxes and mins. Okay, we have the zeros. We can also find the maximums and minimums. So form a table, choose values for theta to get R, those give you the key points. Okay, just take the easy values for theta. For example, I can take 0 for theta. I'm not gonna go crazy with like 5 pi over 6 or pi over 6. Plug in 0 here, you get 1 plus 2, and that is equal to 3. Okay. The next key point is when theta is pi over 2. Basically, take increments of 90 degrees. Okay, pi over 2, cosine of pi over 2 is 0, so we get 1. Okay, next, take pi. Pi, cosine of pi is -1, so we get 1 minus 2, which is -1. That would be the minimum. And 3 pi over 2. Again, cosine of 3 pi over 2 is 0, we get 1. And take 2 pi. 2 pi, you go back to 3. Okay? Again, these are max. We get the max, mins, and some values in between. I call the key points 0 pi over 2 pi, 3 pi over 2, and 2 pi. They're just nice values. Okay, so what you're gonna do is use the key points and the zeros to graph R versus theta. Okay, let me make this a little smaller. Okay, so we got -1, 1, 2, and 3. All right, and again, we're gonna graph from 0 to 2 pi. Okay, so if you want to be more accurate with locating these values on the theta axis, by the way, this is the, we're not, guys, we are not graphing a polar graph yet, okay? We're graphing the rectangular version of this thing. So this is theta, think of that as the x-axis, and this is the r-axis, okay? We're not doing angles and distances. We're just drawing the cosine wave, okay? Keep that in mind. So I'm locating the key points, pi over 2. We have pi. All right. At 0, r is at 3. Okay, so 0, 3 is right here. At pi over 2, r is going to be 1. All right. At pi, it is -1. And somewhere in between, r is gonna cross the theta axis. It's gonna pass its 0, and that happens right here at 2 pi over 3. That is the 0. Count that as one of the key points. Okay, at 3 pi over 2, r is going to be 1. Okay, so we have another 0 somewhere in there, right here, where we have 4 pi over 3. Okay, and then at 2 pi, r is 3. Okay, so again, this is nothing but pre-calculus. I'm not going to focus on teaching how to graph a cosine cycle. Okay, just the graph of cosine shifted up by 1. Amplitude is 2, shifted up by 1. All right. Now, we are going to transform this graph to its polar version. And this is where you really, really need to pay attention, guys. Let me, there we go. All right. So again, as long as you understand this, then the procedure is super easy. Okay. So here's what's happening. As theta, look at that, look at your theta. As theta goes from 0 to one of the key points, pi over 2. Okay, we're talking about this part of the graph. Okay, again, I'm going to color code things so you can associate between the non-polar and the polar. Yeah, so initially at theta of 0, r is 3, here is 0. And if you don't mind, guys, I'm going to count every 2 of these as 1 unit to make the graph a little bigger. So again, at theta of 0, r is 3. So we are right there. And then at pi over 2, r is going to come down to 1. Right there. Okay, so what this says, what this is telling you is that as theta goes from 0 to pi over 2, okay, r is going from 3 to 1. Okay, so here r is 3 and here r is 1. This r is just getting smaller and smaller. It's getting closer and closer to 1. Remember that r is the distance from the pole to any point on the polar graph. Okay, so again, I'm drawing those distances. They're just getting smaller and smaller. So what you get is, imagine you're drawing a circle, okay, but the radius of the circle gets smaller and smaller. That's what's going on basically. So something like that. It's a little too big. Again, this graph is not perfect. It's not really accurate in terms of where the points are, but it describes the behavior. Okay. Yeah, so next, as R goes from right here, let's focus on this part of the graph. As R goes from pi over 2, as theta goes from pi over 2 to pi over 3, R goes from 1 to 0. Let me write it down. So theta going from pi over 2 to 2 pi over 3, R goes from 1 to 0. Okay, so here is 2 pi over 3. What I typically do is I draw a dashed line at the angles where theta is 0. 2 pi over 3 is where R is equal to 0. I just draw a dashed line indicating that this is a 0. Okay, let me actually do that for both zeros. So at 2 pi over 3, we have a 0, that's this angle. Draw a dashed line just for reference. This is where R is 0. Also later at 4 pi over 3, which is this angle, R is again 0. Okay, so drawing this piece of a graph, R goes from 0 to 1 as you go from this angle to this angle. Okay, so we get something like that. All right, look at that, guys. R is 1, and then R gets small and smaller. The distance from the pole to the graph gets small and small. Okay, now here is where things might get a little tricky. Because for this part of the graph, R is gonna become negative. Okay, and this is where you really have to pay attention. So going from 2 pi over 3 to pi, R is gonna go from 0 down to -1. Okay. So where is 2 pi over 3 to pi region? It's this region. From this angle to this angle is where we are talking about. Guys, make sure you're listening, please. From 2 pi over 3 to pi. Here, since R is negative, then you are not going to draw the graph here. There will be no graph here. The graph, remember, is going to be on the opposite angle. Okay, so instead of drawing a graph here, the graph is going to be in this region. Does that make sense? Again, from here to here, R is negative, so the graph will be in the opposite region, which would be this region. Well, let's see how. At pi, or what is it? At 2 pi over 3, R is 0. Okay, but later at pi, R is gonna be -1. So here's theta of pi. If I put, if you look at this point is R equal to 1, but R of -1 would be right here. Okay, so this is the angle pi, but since R is -1, you go in the opposite direction of the terminal side and you put the point there. Okay, and again, as I said, the graph instead of being here is going to be here. Okay, so that's what the graph is going to look like. Make sure that made sense. All right, so now this piece is when theta goes from pi to 4 pi over 3. I'm not going to write this down anymore. But when theta goes from pi to 4 pi over 3, r goes from -1 back to 0. Okay, so we are talking about this region of the plane from pi to 4 pi over 3. Again, since r is negative, the graph is not going to be here, but instead, the graph is going to be here. Okay, so not there, but the opposite vertical side of that angle. Okay, so this piece corresponds to this polar graph, polar piece of the graph, or the piece of the polar graph. All right. Yeah. So we are done. We are done with the part that goes from here to here. Again, there is nothing right there. Instead, the graph is here. Now r is going to become positive. So as we go from 4 pi over 3 to 3 pi over 2, we are talking about this piece. Okay, r goes from 0 back to 1. See, at 3 pi over 2, r is equal to 1. Here is 3 pi. Here's 3 pi over 2. Angle r of 1 will put you right there at that point. Okay, so we get this piece of the graph. All right, almost done. Last piece is this piece here, where r goes from 1 back to 3. So as we go from this angle to this angle, r is initially 1. It's just going to get big and bigger and go back to 3. All right, and that is the polar graph, and this graph is called a lemicon. It has an inner loop. All right, that inner loop is because of r being negative. Anytime r is negative, graph will loop. So before you go, please pay attention to the orientation, like how this is graphed. This is the orientation. Now that loop, exiting that loop. So one more time, r is positive, r becomes 0, r is negative, r here is -1, r is negative, but going back to 0, now r becomes positive, r here is 1, r is going back to 3. Okay, anytime the Cartesian form of the graph is below the x-axis, below the horizontal axis, you get a loop. Okay, so that corresponds to the loop. See you tomorrow.
Thank you.
Professor.